Okay, let's get started. Okay, so I spent some time preparing for some Zoom setting. It's not easy actually. Sorry about that. So in the previous class, we discussed about the semiconductor technology, and we learned how most transistor works. And then also we discussed about some very important issues in the computer architecture research field. So that was the power consumption. So actually the power consumption is very critical problems in the computer processors and the computer systems, because as I mentioned, that the power consumption of the processor determines the manufacturing cost. Also, it determines the running cost of computer systems. So actually, it's very critical. So then, actually the power consumption issue is influenced by some semiconductor technology node, and then recently the technology node have advanced to shrink the channel length of the most transistor. But by doing this, and the static power consumption have increased. So actually, recently, the static power consumption occupies the large portion of the entire power consumption of the processor. So that's why the static power consumption is also critical for the some architecture and then also the process of design. Actually, so we can solve this static power consumption issue with some design techniques and then also architectural techniques. Sometimes the multi-core processors can turn off some power domains, so like some cores, independent cores, to reduce the static power. So I said turn off, so which means that the supply voltage, so actually the power delivery line is cut off in the inside of chip. So actually there are many techniques to reduce static power consumption. Okay, so it's very important research area, architecture, also in the system design. And then today I will discuss about some more issues in the it's related to the semiconductor technology node. So I will briefly discuss about the reliability issue in the process architecture, and then we will move on some architectural issues, more architectural issues such as the instruction set architecture, and then also I will lead the static pipeline architecture. So this static pipeline architecture is actually, so you are familiar with the static pipeline architecture because we learned the 5-stage pipeline architecture in the undergraduate course. But in this time, I will also review this 5-stage pipeline architecture. Also, I will discuss about some more advanced architecture, such as superscalar or super pipeline architecture. So hopefully I can complete until some static pipeline architecture. Okay, so let's discuss about the reliability. And then, as I mentioned in the previous class, so reliability means that the data in the computer processor can be changed. So actually, we assume that the data inside of this processor does not change because we are using the digital design. So which means that digital design is it's very tolerant to the some noise. So noise signals. So which means that actually in the digital signals, the output of the digital signal is determined by the threshold level. So threshold that is some threshold level, and then if the signal level is higher than this threshold level, then we can say that this output result is 1. And then if it is below the threshold level, we can say, oh, it's 0. And then, actually our world is analog world, so that means that every signal is continuous, but so we are using a digital system, so which means that the signal is discrete. So, and then also these signals are very tolerant to the noise. But the problem is that even the digital data can be changed, and then there are many issues, many reasons why the digital signals or digital data values, digital values change it. So one of the issues is that actually I said that in the semiconductor technology, the level of the digital value is determined by amount of charge. So which means that this amount of charge changes, and then if this change is below some threshold level or it's higher than the threshold level, then the result of our digital data can be changed. And then that's the problem. Also, the reliability issue is getting more critical because, as I said, the technology node is advanced, so which means that the channel length, also the size of the transistor is reduced, so which means that the amount of charge stored in this capacitor also decreased, so which means that this amount of charge can be influenced by some outer effect, some outer noises. So that's why the reliability issue is getting more critical for especially for the modern semiconductor technology node. Okay, so let's talk about the reliability. Okay, as I mentioned, the reliability issue is getting more critical because the transistor size is being decreased. So also, what is the issue of this reliability issue? So one of the reliability issue is that the one single chip includes the more transistors. So what does that mean? So if the more transistors are included in the single chip, then the error rate of this single chip can be increased. So why? So many components are included, and then if the one error is detected, or one error occurs in one of these components, then we can say that error is detected in our processor. So that means as many transistors are included, then the error rate can be increased. That's another some issue of this is the also why the reliability issue is getting more critical for the modern semiconductor technology node. Also, as I mentioned, most transistor size is getting decreased. So size is reduced, so which means that the amount of charge, also some supply voltage, and then some threshold voltage is also reduced. So which means that if some noises are included in our transistor devices, then the charge can be fluctuated. So the amount of charge can be changed. So it's more susceptible to soft errors. So soft error means that it's not hard error. Hard error means that the error will be permanently occurs in the devices. So that is called the hard error. But soft error means that the error can be generated due to some noises, some other outer issues like outspace radiation. It's ridiculous, but it's true. So it's more susceptible to soft errors. Okay, and then another issue, the wear out issues. The wear out issue means it's, so we can say that our devices or our clothing worn out. So worn out means it's getting worn out. So 낡아지는 거 말해요. 낡아지는 거, worn out. So it may sound weird because our transistors or our electric devices are worn out, but it's true. Actually, the property or characteristics of CMOS transistors gets worse from the first manufacturing. So it is because the device characteristics are getting worse. So it is called the wear out. And then also we need to consider the wear out problems in our processors. But actually for the personal user computers, the wear out issue is not a critical issue because we do not use our devices frequently. But maybe you can see your smartphone every day or every hours, but it's not. It's different from the server system. So think like the server systems. So if server systems are always turned on, and then server systems are always run the many applications, and then so actually the reliability issue is very critical for server systems, not the personal use or mobile computers. Then also we can also think about the reliability issues in the memory devices. So the memory devices store our digital data, and then so so if we just consider these memory devices, so think like the DRAM, like this DRAM. Sorry. If we just consider the DRAM, so so the data of the DRAM is just to store this capacitor. And then if the DRAM size is reduced, then also the amount of charge stored in this capacitor is also decreases. Which means that the data inside of modern DRAM devices is more susceptible to soft errors because the charges can be changed. So it is also true for those modern memory devices such as flash memory. Okay, so also the reliability issue is very critical for this flash memory. And then, but if we just think about the change of data inside of the processor, but this change of data does not occur errors, does not always occur errors. What does that mean? So think like this. So this is the memory devices, and then our data is stored in these memory devices. But so because of some outer issues like radiations, the data inside of this memory device changes. But this data is not consumed by our application. It can be possible. So the data is already used, and then the data can be stored in the internal memory, such as cache. So even though this data is changed, the changed data does not occur errors in our processors. So in this case, the error happens, the data is changed. The change of data does not cause any errors in these systems. Okay, so actually the reliability is not a easy field. That means that it's a little bit tricky because as I mentioned, data can be changed. So we can say that, oh, if data is changed, that means that its bit is split. Then, oh, we can say that, oh, error is maybe data error is data error, of course, in our memory devices. But this error does not, these errors are not harmful because it does not cause any faults or does not cause any errors in our computer systems. So we need to distinguish this kind of errors. So think like this. So we need distinguish the fault and errors. So think like this. Consider this slide. So think like this. So some data is stored in our processors or memory components. So you can say that, oh, some data bit is read or not. If the data is not read, that means that, oh, this data is not consumed by our application. So even though the device is like the data inside of this memory is changing, but if this data is not read, it's not error. So it is called benign fault. So it's not harmful, but and then it does not cause any errors in our computer system. But if the data is read, but the errors can be detected. Okay. So think like this. So you can, in a server computer system, you can use the ECC DRAM. Okay. So, and then we frequently apply the SecDat for our ECC DRAM, which means there is a single error detection, then some single error correction and double error detection. Which means that if a single bit error is detected, then this error can be recovered. Okay, this error can be corrected. So even though the bit changes are detected, and then if these bit changes can be corrected, this is not an error. Okay, because it is correctable. Okay, so but things like that. So actually double errors can be detected, but these double errors cannot be corrected with our ECC DRAM. So the error is detected, but error is not corrected. When in this case, the errors can be harmful, but we can also distinguish the result of our applications. If these errors, so the detected errors changes the out of our application, then we can say that, oh, it's harmful. But if the detected errors do not change the result of our applications, so we can say that, oh, it's not an error because it's not harmful. Okay, so we can, based on the output of our programs or applications, we can say that, oh, this is a true DUE. DUE means that detected but unrecoverable error. Okay, but if this detected fault, actually it's a fault, detected fault does not change the output of our application, then we can say that, oh, this is false DUE due. Okay, so we can also distinguish, oh, error can be detected, but error can be corrected. Also, error can be detected, and this error is not corrected. But we can also distinguish the output of our applications. So which means that bit can be changed. Bits in some devices or memories can be changed by some noises, due to noises. But this is not called errors because it's not harmful, because it is determined by architectural, the process architectures. Also, it is determined by applications. And then even though error is actually the people, the faults occurs in our processors. But if these faults are not harmful in our systems, we cannot say, oh, this is error. Okay. Also, even though, so we can say that these bit flips or the data change is not protected, so it's not detected. So, but these faults can also change the outcome of our applications, or it may not be harmful. Okay, so if these faults are not detected or faults are not protected, then we can say that this is the silent data corruption, called the SDC. But even though, as I mentioned, even though these data faults are not detected, this may not be harmful in our system. So we also distinguish these two cases. So actually, in a system view, what is critical? The critical error is the SDC and true due. So actually, we need to consider these two factors in the reliability of computer systems. Okay, why? If we just reduce the bit error rate or some data fault in our computer system, we need to invest some resources, like the hardware resources or architectural resources. So which means that the computer processors can be expensive if we just invest some resources to our processors to reduce the bit error rate. But even though the bit error the bit flips can happen in our computer systems, but these bit flips are not harmful in the computer system. So in this case, we can ignore these bit flips. So that means we can reduce some investment of our efforts for reliability in our computer system. Okay, so we need to consider these factors. So actually, the software rate called the SER is the SDC plus DUE. And as I mentioned, the SDC is the silent data corruption, and then DUE is the detected and unrecoverable error. And then when we measure the failures in our computer system, we frequently use the MTTF. Actually, it's MTTF. We can find the MTTF frequently in the SSD specification. That is MTTF. So mean time to failure. Okay. So that means that the mean time to failure means that failure happens for some time, and after some time, like this mean time, when the average of the time, so another failure can happen. So this is the definition of mean time to failure. So which means, so 1 year MTTF means that so one error can happen during 1 year. Okay, so that's the definition of MTTF. And then you can use the FIT, so which means the failure in time. So that counts the number of failures in some specific time. And then 1 bit, the definition of 1 bit is the 1 failure in billion hours. Consider the billion hours. It's a very long time. So 1 year MTTF is equivalent to this, how can I say? So this FIT, okay? So we can use the MTTF or FIT for measuring the reliability of computer system. Okay, and then as I explained, the data bit error rate. So it's the data bit flips can be correctable, or it is detected. It can be detected, or it cannot be detected. So for example, as I mentioned, we can use the secdet code in our memory systems. And then, so in the actually in the ECC DRAM DIMMs. So with the secdet, so as you can see, secdet means it's a single error correction and then double error detection. So which means if the one bit flip happens in our this entire memory row read, then we can recover this one bit error, okay, with the secdet. And then if the 2-bit flips if a 2-bit flips occurs in some entire row read, not the entire row, so some data read from the ECC DRAM, then we can detect this error, but this error is not corrected. Okay? It's just a detection. How about the 3-bit flips? The 3 bits are flipped, then we cannot detect. Also, we cannot correct this error. So it can cause SDC. So so it can cause some errors, but as I mentioned in the previous class, this slides, it may not be harmful. Okay, it is determined by some states of the processor, so some states of applications. Okay, and then when we say about the reliability of a computer system, then we can frequently use this plot. It looks like boat. So sometimes it is called the boat plot. It's boat shaped like this. So we can encounter higher failure rate in the early, and then these failures are called early failures. And then these failures occur during the manufacturing. So think like this. So this is the processor. So we can implement our process on some silicon wafers, and then so which means that the silicon wafers may have defects. Okay. Now, so during the manufacturing processes, and these defects can be added to our processor chip. So usually during the manufacturing, some errors can be included. And this is called the early failure. So it's also important because we frequently use, say, the yields of the semiconductor processing node. So as you know, yield is actually very critical for the benefit of some industry, the semiconductor industry. So the industry should be high, so we can actually the components can earn money. But during the manufacturing, some faults can be included in our chip, and then actually these faults can be detected by some test and verification of our processor chip. So, and then this is called the early failures. And then usually the failure rate is high during this early stage of our processor chip. And then some errors are detected, some failures are detected, and then actually it just threw away some failed chip. So it's called stone because silicon is just actually it's just sand. So it is called stone. So it's not working properly. And then during the lifetime, so actually the failure rate is usually low because some failed chip is removed in this early stages. So we just used some chips that works normally. So, and then random failures can happen during this some useful lifetime. And then after some time, after some very long time, devices are worn out, which means many failures can occur during this later stage. So these are called the one-out errors, wear-out errors. Okay, wear-out errors. So actually, the failure rate looks like this graph. So this is called the both graph. Okay. And then I briefly explain about some failure issues in the semiconductor devices. So I'm not an expert of this reliability research, so I will briefly explain about some these failure issues. So first, I explained that some faults, that means the big flips, can be caused by space radiations. So which means that actually we cannot see some particles from the space, but actually many particles are hitting the Earth, okay, from space. So it's also that's true for our transistors or digital devices. So many particles are hitting our devices, digital devices or computer chips or memory chips. And then if these particles hit the transistors or some memory devices, the charge amount of charge can be changed. Okay, and this is and then if the charge is changed and then if it is changed, it exceeds some threshold level, then the data inside of this processor chips or memory devices can be changed. So actually, we can say neutron strike. So which means some particles, so neutrons from the space or some our air can hit our processors or memory devices. So the data inside of our processor or memory devices can be changed. This is the soft event upset. Where actually most of the reliability it's a software. And then okay, so actually we can consider some other reliability issues, but if we just study on the reliability in computer systems, then we can just focus on these software errors by radiations. So this is the software error rate equation. We cannot. So as I said, as I'm not an expert of this reliability research, so if we can just see this equation, and then we can say that the reliability is determined by these factors. Okay, so this is the software error rate equation, and then as you can see, this is proportional to the flux. Okay, so and then the interesting thing is that flux depends on altitude. So altitude is a godo. So which means because this software error rate is influenced by radiations from space, and then that means if our devices are on the high altitude, then it will be exposed to some more radiations from space. So that's why the flux depends on altitude. So which means that software error, the more software errors can happen in the high altitude. It's interesting. Okay, so it means if our devices are on the, if we just bring our devices on the very high mountains, then it will be high. It will be more influenced by radiation from space, and it will cause more software errors. It's interesting. Also, bit area. So bit area is depends on bit area depends on the technology node. Okay. And then important thing is this Q. So this is the some depends on some technology node. And then important thing is the Q critical and Q correct. So Q critical means that is the charge needed to flip a bit. So then, as you can see, Q critical is proportional to capacitance and supply voltage. So then what's the issue in the more advanced semiconductor technology? So capacitance is reducing because the size of a transistor is also decreasing. Also, here the supply voltage is also low compared to the old devices. So C is low, and then C node is low, so which means that Q critical is also low, which means that the bits of the error rate increases because our device is getting smaller. Okay, while the reliability is getting more critical in some modern devices. But so we are talking about the architecture, the process architecture, and also we need to consider the architectural vulnerability factor. Okay, the architectural vulnerability factor means that it's the probability that bit errors. So as I mentioned, bit errors can happen in our devices or processors or in memory devices, but we can say that, oh, these bit faults can change our outputs, and this is the error. But because of some many issues like architectural issues or some application issues, even though this bit fault does not change the result of the system. So which means that this is not harmful. So we need to consider the architectural issues when you say about the vulnerability. So it's like errors in the computer systems. And because of some architectural features, even though the bit flip happens, it may not be harmful. Okay, so we need to consider this architectural vulnerability factors. So actually, the error FIT of the bit is the intrinsic FIT. So entire fault by some bit flips, and then we need to also. And then this is multiplied by AVF, is architectural vulnerability factors. So we can just set up this AVF as the 100%. So which means that every bit flips, every bit faults are protected by architecture. Okay, we can design our processor like this, but it can be waste. Okay, so this is but it is also influenced by some semiconductor technology, and then some also some size of transistors. Okay, so actually the semiconductor technology. So this is the as this feed, then okay, so this is the as this FAT, and then you can say that this is the some time. So you can say that the semiconductor advances by time, and then this is the graph. So this is the IBM goal. So there's a goal by IBM. Then so you can see that. So let me see. So this is the target of the IBM company. So we can, so IBM company try to maintain the SD speed as the 100 here. Then this is the goal, but it depends on the some semiconductor technology and then some architectural effort for this for processor. Okay, so if we just okay, so SDC should be lower than the just this assumption maybe. So sorry about that. I need to fix the my explanation. So actually, this is the probability of that bit errors. So which means that AVP means that bit errors, like a bit fault, can affect the affects the errors in the computer system. So if you assume that every error change the output result of our computer system, then we can say that this is the AVF is the 100%. Okay, but it's not true as I explained. But that's our assumption. It's a design target. We can say that, or we can assume that, every bit fault affect the result of our computer system. So we can then we need to invest some our efforts and then some architectural efforts or some design efforts to reduce the some failure rate. Okay, and then failure rate is the FIT, but it's not true. So we need to if we just decrease this value, then we can invest some lower efforts, so lower resources or lower design efforts to our system. Okay. So this is the goal of the IBM, and then it also assumes that it's 100% vulnerable and then 100% AVF. So if the system is 100 vulnerable and then we assume that this vulnerable, so the default affect the output result 100%, then this is graph looks like this. And then as time by time, this graph is exponentially increases. So because this is the log scale. So if the system is very vulnerable and then it's every fault affects the output 100%, then it looks like this. So we cannot meet the goal set by IBM. So this 100 feet. But if this is error rate, so this is 20% vulnerable, but it's the 100% AVF. The graph looks like this. Okay, so we can also based on some vulnerability and then AVF effort, then we can AVF assumption, then we can also set the goal like this. But as you can see, even though this year, even though the vulnerability is low and then the AVF is just 10%, so we cannot meet the target by this IBM goal. Okay, so that's the problem. Okay, so okay, and then as I mentioned, when we consider the architecture issues of the reliability, then we need to also distinguish the architecturally correct execution and then on-ACE bits. So on-ACE bits means that even though the bit data is changed, this change of a bit flips are not harmful. Okay, so this is some example of the on-ACE bits. Okay, like the idle or invalid state. So we can define some states in our design like a idle state. So if we just make FSM, then we can define some states with the state bit. But most of the case, so some states we can define some specific spaces like with the FSM, but we cannot use the entire bit. So entire some entire state using the our bit data. Okay, so which means this FSM has some idle or invalid states. Okay, so in this case, so even though some bits are changed, and then if the bit changes does not change, if the bit changes do not change the states of our FSM, it's not harmful. Okay, it's some example of on a bit, and then misspeculated states. So speculation is critical for the performance, but even though the speculation fails, it's not harmful for the result of our computer systems, right? It's just speculation, it's some prediction. So even though the prediction is not successful, it's not harmful for the output result of our computer system. Okay, so even though the speculation is influenced by some errors by the beliefs, this is not harmful. Okay, also it's true for the predictors like branch predictors or return address stacks. Even though these predictions are not correct, but it's not harmful. Okay, and then dead bits. So dead bits means that, like as I explained, the data is stored in the register file or memory devices, and then what is already consumed, and then it will not be reused. Then even though this data are changed, it's not harmful. Okay. So this is some architectural honest bits. So we need to distinguish these honest bits in the microarchitecture. Okay. So we can also actually there are many components. So there's actually in our computer processors, so we just add some many architectural techniques to improve the performance. But the most of the performance is based on the prediction or speculations. And then, but even though these speculations or predictions are influenced by some beliefs, but it's not harmful. So we can also think like this honest bits. Okay. Then these are some where our issues of the issues in our processor design. So actually it sounds very weird. So I discussed about the electro migration. It sounds very weird. Why? Actually, this reliability issue is the very low level issues, but it's very. So if we just say about some wear out of our circuits, then these issues should be considered. Okay, so actually wear out is also very critical issues for the server chips or server computers, because if we run our server system for a very long time, then the performance, usually the speed of our circuit or some performance of our circuits is also decreased. So this is due to the wear out issue. So if the wear out issues are detected, then the performance of the circuits are also decreases. So which means that we need to reduce the clock frequency of our circuit, because the critical path, the delay of the critical path increases by wear out issues. So I will show some example of what these wear out issues in some CMOS devices, but it sounds very weird. Okay, the first wear out issue is the electro migration. So electro migration is that the wire is metal. Wire is you can make wires with metal, So that means that this is the conductors. Okay, so conductors means that these wires includes the many free electrons. So, but if the current flows the one direction for a long time, then the electrons are dissipated from this wire. So that means that the electrons can be reduced, and then the wires can be cut off. Okay. Also, the electrons dissipated from some adjacent wire is added to the neighbor wires, and then the width of this wire is increased. So that can happen. So this is called the electromigration issue. So there can be two different phenomena, like the void creation and then hillock deposition. So void creation means that the width of the wire is reduced, and then this wire is cut. So that means that the currents cannot flow through this wire. So this is called the void creation. And then hillock deposition means that the wire width is increased because of this issue, the electromigration. And then if this wire is the width of the wire is increased, then like this, the wire can be short with the adjacent wires. So which means that the wire is the two adjacent wires contact each other. So this is short of the circuit. So that can be the critical issue. So which means that the metal wire is cut off, or some two metal wires with each other. So it causes short in a circuit. Okay. So this is the electromigration issue. And then sometimes we can consider this electromigration issues in the SRAM cell. So this is the SRAM cell, and then you can see the bin line here. And then when the data is read from these SRAM cells, or also you can know that the many these cells are attached to this bin line. Okay. So as the data is read via these bin lines, the current flow this direction. So if we just compare some current level and then direction of the electric current for this line, then we can find that the current looks like this. So and it's very short time here. So which means that for this direction, the more currents flow this direction, or more, okay, for longer time, which may cause electromigration in the SRAM cell. So the electromigration is due to the electromigration, the circuits can be broken. Okay, and then negative bias temperature instability, and it's called the MTTF. Which also very, but that can be, it's also another wear out issue. Then also it's very related to some materials of most transistor. So actually, so when the negative voltage is induced to this gate of the PMOS transistor, then holes can be captured to this gate of the PMOS transistor. So you can see that this SiO2 is the insulator. So you can say that through this insulator, the dielectric, then the holes cannot move to this gate. So gate is connected to the metal layer, but because when this voltage was negative, some holes can move to this gate, the metal gate, and then the holes can be captured in this metal, okay, metal. And then if this is not recovered, so that means that the holes are trapped into this metal layer, then the gate voltage is influenced by higher threshold voltage. So that means that we need a more higher threshold voltage to work this PMOS transistor. Okay, so sometimes this can be recovered, but for this recovery, we need a long time. Okay, so this is the negative bias temperature instability. So which means that actually we can. It's not easy to explain because we are not an expert of the semiconductor devices. Okay, it's a kind of some material engineering or some physics area. So it's not easy to explain, but we can say that when these PMOS transistors are used for a very long time, then the characteristics of this MOS transistor is getting worse. Okay, so it means that the threshold voltage, we need a higher threshold voltage, which means that the characteristics is getting worse. So this means that the transistor is the performance of the transistor is getting lower. Okay. So another issue is also time-dependent dielectric breakdown. So it's also similar to this MBTI issue. So which means that this is the dielectric. So which means this is the insulator. So, but for some reasons, the holes are trapped in this insulator. So it also influences some voltage level of this gate. So which means the property of this MOS transistor is not good. Okay, so this is another real issue. Because this reliability issue is a very low level issues. We are not familiar with this low level issues, and then also the device issues or material issues in our semiconductor in our processors. Okay, but so we can focus on these reliability issues because for the modern devices, the reliability issue is getting more critical. Actually, for memory devices like the DRAM or also the flash memory, the reliability is getting more critical. So think like the DDR5. So with the DDR5, we can use the higher bandwidth with the high working frequency. But the DDR5 now has ECC code. Okay, in order to support some high speed of our DRAM teams. Also, so that means that reliability is critical. Okay, the DDR5 can support the very high performance DRAM teams with the high clock frequency, but high clock frequency cause more reliability issues. So that means that the data, if the data is read from this DDR, like DRAM, the data can be changed. And then in order to avoid this issue, then ECC engine is included in the DDR5. Also, the another issue is the refresh in DRAM. The refresh is also very critical because if actually the electric charges in this DRAM capacitor is dissipated by time. And in order to recover these dissipated charges in the DRAM capacitors, we need to apply the refresh. But refresh is also very critical for the performance of DRAM because during the refresh period, we cannot use these DRAM devices. So it's very critical. But refresh is also related to the reliability issues. And also, the flash memory. the flash memory is one out and the flash memory cell is erased. Also, currently some flash vendors such as Intel just sold their flash. Okay, so SK or Samsung developed the QLC, which means that in a single flash memory cell, we can store 4 bits of data, but this is very critical. So these are very vulnerable to the wear out of this memory cell of the flash memory. Okay, so it means that for the QLC device, we can just erase around less than 1,000 times. So which means that the characteristics of this flash memory cell gets worse by erases. So usually the reliability issues are very critical for the memory devices because the memory devices store a large amount of digital bits inside of its component. Okay, so we can also focus on these reliability issues because reliability issues are getting more critical. Okay. So let's take a break for 10 minutes, and then I will be there at around 11:48. Okay, so let's take a break. Okay, let's get started. So actually, so it is, even though we discussed about the reliability issue of the computer systems, it's actually it's reliability. Not to understand the reliability issues on the computer systems, actually, we need to know about some very detail of some semiconductor devices or some not very detailed, but so actually the reliability issues are related to some detailed aspects of the most transistors or memory cells. And then first we need to understand some property of this most transistors or some property of memory cells. So it's a kind of some low level issues. So I think most of the students are not familiar with some reliability issues. Okay, so now we are moving on the instruction set architecture. It's the higher level of the computer systems. So I think it's more familiar. Okay. So actually, so this is the outline of the today's class about the instruction set architecture. But I believe that most of you are familiar with the instruction set architecture because we learned about the ISA in the undergraduate course. So what is the instruction set architecture? So actually, when we define the computer architecture, so we can the area of the computer architecture looks like this. When we mention the computer architecture, then traditionally it mentioned the instruction set architecture. So it's the and then also we can explore the computer system organization, how to build our computer systems. Also, we can focus on the process architecture or architecture of memory systems. So these are the area of computer architecture research field, but in this time, we will focus on the instruction set, so called the instruction set architecture. So in the undergraduate course, I explained that instruction set architecture is the interface between software and hardware. Okay, so that means in the instruction set architecture, instructions are defined. So which means that actually when we mention the computer processor means that this computer processor receives instructions and then processors generate the result defined in for instructions. And then these definitions are defined in the instruction set architecture. So for example, like add instruction. So we can define the add instruction in the instruction set architecture, and then so everyone knows the result of this add instruction, like add R1, R2, R3. So the result is that this add instruction is operand from the source registers R2 and R3, and then the results are stored in the destination register R1. That is the definition. Then this definition is listed in the instruction set architecture, and then computer processor, the hardware implements these definitions. So that is the result of instructions. That's why the instruction set architecture is called the interface between software and hardware. So software design and the software actually, this is some area of the compile actually. So actually we just write our code with the high-level languages, high-level programming languages. And then this code written in high-level languages are compiled by compilers. So compilers generate the machine codes, and the machine codes includes the instructions. So these instructions are given to the computer processors, and then computer processor is the hardware generate the result defined in both instructions. Okay. So this is interface between software and hardware, and then usually the ISA is related to the operating system and or compilers. Okay. And then so we can design these instruction set architectures, and then conventionally, when we mention the computer architecture, I think it is defined. It mentions the instruction set architecture. So which means that we need to design instruction set architecture for building efficient software and efficient hardware. Okay, and then some important issue is the backward compatibility. So backward compatibility means that if a certain high level code is compiled, and then binary code is generated, okay, by this compiler, but this binary code should be executed by old computers or some modern computers. Okay. So, which means that if this binary code is compiled using x86 architect ISA, and all x86 processors need to run this binary. Okay? This is called the backward compatibility. So sometimes the instructions can be inefficient. So it's also true for the x86 instruction set architecture. So x86 instruction architecture is a little bit inefficient because it was invented a long time ago, and then so these instructions includes the very inefficient instructions, like some so actually the instruction length is variable, various, and then also the instructions can be very inefficient. But modern x86 processors also need to support these instructions, okay, even though instructions are very inefficient. So this is called the backward compatibility. So which means that if once binaries are generated by some compilers, all kinds of processors that support a certain ISA need to run these compiled binaries. Okay, it's the backward compatibility. The backward compatibility is also important for the commercial ISA. Okay, so we can categorize the instructions as some different classes. And actually, it's some review of the undergraduate computer architecture course. So we can use the integer, arithmetic, or logic instructions like add or solve instructions and multiply instructions. Also, we can use the logical instructions such as OR and OR NAND. So these are the logical. So these logical instructions perform some logical operations. Also, we can define the floating point instructions like fadd, fmove, fdiv. So, so there are two different data types, so like integer type or floating point type. So, and then in the undergraduate computer architecture course, we learned about the integer type data, and then we learned about the floating point type data. Actually, the two data types are default. So actually, integer type instructions requires the integer type processing engine, like integer type ALU, and then floating point. For the floating point instructions, we require floating point type ALU. So floating point, actually these are called the floating point units. So the different type of processing engines are required. So usually integer type instructions can be the base instructions of ISA. So it's true for the RISC-V ISAR, because for the RISC-V ISAR, the base instruction set architecture just supports the integer type instructions. And then we can also add the floating point type instructions as an extensions of base ISA. Okay. So because in order to support these floating point instructions, we require additional register files. It's a floating point register files. Also, we require a floating point ALU, so floating point units. Okay, so the property of this floating point ALU is a little bit different from the integer type ALU, because the floating point data type is more complex than the integer type data. So that means the hardware is also more complex. So which means the delay, the latency of this floating point unit is usually it's much longer than the latency of integer type ALU. And then we need the memory transfer instructions and load and store instructions. Also for some atomic operations, we need to support the test and set or swap instructions. Okay, so these instructions are used for some synchronization or some implementation of the barriers. Okay. Also, another class of instructions. Another class of instructions is control instructions. 종이 있었군요. 그럴 때. Control instructions. So we can change some flow of instructions like if, as. So this is the example of the some conditional branch, if then as statement. So based on some conditions, we can change the statement executed by these conditions. And then so which means that based on these conditions, some instructions for this statement can be executed. Also, another instructions for this statement can be executed. So which means that we need to change the program counter of our programs. So in order to support this conditional branch or some if statement of some high-level languages, and the ISA supports the control instructions. Then usually we use the branches or jump instructions for these control instructions. the branches are conditional. So conditional means that the performs the result of the branch is determined by some conditions. So like so we can check the equality of two registers. Also, we can check the not equal of the two registers, two data. So we can use some condition bits like a G, C, B, X, N. Okay. So which means that if a certain instruction is executed, the condition bit can be also changed. Okay. So and then based on these condition bits, the result of branches can be also determined. Okay. And then jump is the unconditional branch. So which means that the PC is always updated by target of jump instructions. So we need to distinguish the branch and jump instructions because branches are conditional and then jumps are unconditional. So this is default. So these are the control instructions. So we can say some different type of operands, the operand of the instructions. So this is the very old type instructions, like accumulator instructions. So add A, add accumulate A. So we can also implement this type of accumulation instructions. Okay, accumulate instruction means that we just accumulate some values to some accumulation registers. Okay, so add A means that the data is read from from the main memory by this memory address, and then this data is accumulated to some specific registers, so accumulation registers. Okay, also we can implement the stack. Stack means that the first in, last out, the data structure, and then we can also implement the stack without the CPU with some operands. But this is the typical. This is not. These are not typical instructions. Okay, because we are familiar with the RISC type instructions, and then usually the RISC type instructions, the data in the memory is handled by only memory transfer instructions in the RISC type instructions. Okay, this is some old type instructions, and then registers. For the RISC type instructions, some instructions usually handle data in registers, so general purpose registers, like load instructions, store instruction, add instruction. So as you can see, these instructions handles the data in these registers. So you can see, if we see that this load instruction need data from the main memory, and then the read data is stored to this destination register. And then we can also this add instruction, you can just handle the registers. This add instruction is data from the two source registers and then store the result to the destination register. So another add instruction, so it's different. So because this is not a typical RISC type instruction, but RISC type instruction, the arithmetic instructions can also handle data in the main memory. So this instruction means that the data is read from the main memory, and then it's added to the data from R2, and then the result is stored to the R2. So usually in a RISC type instruction, the data in main memory is only handled by memory transfer instructions, data transfer instructions such as load and store instructions. But in a RISC type instructions, arithmetic instructions also can access the data in main memory. Okay. Okay, and then another data type is the immediate data type. So immediate data type means that this immediate data means the very small constant number, and then this immediate data is included in the instructions. So actually this is the assembly instructions, and then actually this assembly instruction need to be translated into the machine instructions, and then actually machine instructions is composed of digital data, the binary data. So which means that some immediate number is included in this instruction, okay? Because this is the small constant number. And then because we frequently use the small constant number in our programs, it's good for support the immediate operands in the instructions. And then we run during the undergraduate computer architecture course. And then operand alignment. And the instructions access the data in the main memory. The data in the main memory should be aligned. So most of the computer processors use the byte address, which means that address 1 occupies the 1 byte. Okay. And then we can define the other different type of load, so data transfer instructions based on the size of data handled by these instructions. So for example, we can indicate the size like LB, LH, LW, LD. So B means the byte, and then H means the half word, and then W means word, and then D means the double word. So, the byte is the 1 byte, so 8-bit. Then half word is the 2 byte. The word means the 4 byte. Then the double means the 8 byte. So we can specify the size of operands in the load instruction like this. And then usually operand of size S must be stored at an address is a multiple of S. Okay, so which means that if we just use the load word, then the address handled by this load word should be multiple of 4 because the word size is the 4 byte. Okay, so which means that the data can be aligned. Data should be aligned in the main memory. Okay. But the RISC-V is a modern instruction set architecture. So actually, the data address it can be aligned, but we don't need to use the aligned address for some different size of data transfer instructions. So for example, load data, load double word. So actually, the load double word handles the 8 byte of data, but in the RISC-V, the address handled by this load word does not need to be aligned by multiple of 8. That is the feature of RISC-V instructions. But usually, if we just handle some specific size of data like a word or double word or half word, then the address accessed by these instructions should be aligned. So that means that the multiple of the size of data. Okay. So it's defined in the instruction set architecture manual. Okay. So compiler is responsible for aligning operands, and then hardware also checks some limitations of this data alignment. Which means that for other instructions and architecture such as if we just support the ARM architecture, ARM ISA, then the memory address to be aligned. So I mean that the hardware needs to check the address of these data transfer instructions. But in RISC-V supports the unaligned memory accesses. So it means that the hardware needs to support the alignment of this data type. But hardware needs to support some data transfers for the unaligned addresses. So addressing mode. So there we can think some different type of addressing mode. So actually we are familiar with these three type of addressing modes because we learned about the risk type ISA in the undergraduate course. So the first addressing mode is the register type, so it's very familiar because so in the arithmetic instructions, we just read data from those two source registers, and then so you just read data from the registers, and then immediate. We can use the immediate type data like this. Also displacement, and actually for the data transfer instructions, like for the risk type ISA, we just frequently use this displacement type addressing mode. So like the address is calculated by offset plus the base address stored in the register file. So we are very familiar with these three types of addressing mode. But the CISC type ISA may support some more complex addressing mode like this. So register indirect and then indexed. So indexed so the index of the memory is computed from the data in the two source registers like this. Also, it's a register indirect. The memory is accessed by the address in the registers. Okay, so the address is also computed from the two source registers like here, and then also direct access with the address and memory indirect, blah blah blah. Also, for the control registers, for the control instructions, the PC is changing. Okay, so we can also use this PC relative addressing mode. Okay, so there are different types of addressing mode, and then, but addressing mode is optimized for supporting the common cases. So the important rule for the computer architecture is the common case first. So which means that we just optimize the common cases. So that means that the frequently used cases. Okay. So that's why the risk type ISA supports only some small number of addressing mode. And then actually these addressing mode can be implemented using multiple instructions. Okay. So even though the risk type instructions supports some small number of instructions, so that means that the risk type ISA supports these three types of addressing mode, and then actually the risk type ISA does not support this different type of addressing mode. But we can implement actually the compiler. Compilers can implement this complex addressing mode using the multiple instructions. And then the number of instructions, the instruction count can be increased, but it's not good for the performance because if we just measure the performance of the computer system, it's the inverse of the execution time. You know, but the execution time is the instruction count multiplied by CPI multiplied by T, the clock period. But so which means that if the risk type in ISA does not support the complex addressing mode, and then I said that these complex addressing mode should be implemented using multiple instructions, which means that if we use the risk type ISA, I see the instruction count may be increased compared to the CISC type ISA. But it may be good because in order to support the complex instructions, the CPI can be also increased. So CPI is a critical for the performance. Also, if the hardware is getting more complex, then the delay, the delay of the critical path can be also increased. So it's not good for the performance. So if the hardware is more simple, then the hardware is more simpler, then we can reduce the clock period, which means that we can increase the clock frequency. It's good for the performance. So if we just consider the instruction count, the RISC type ISA is not good. It's not a good option. Which means that if we just reduce, we can just reduce some instruction count using the RISC type ISA. But it's RISC type ISA is good for the hardware implementation or some CPI. Okay, so then like this, and then but another disadvantage of the RISC type ISA is the number of available registers, architectural registers. So which means that if we just use more instructions, then more instructions may require more register files. So which means that the computer processor needs to have more architectural registers, not physical registers, more architectural registers. So, the registers are very precious resources. If the registers are occupied by many instructions, then we need to replace the data from these registers. And then if the data should be maintained, then we need to store this data to the main memory, not register file, because of the pressures in the register file. So that is another disadvantage of the RISC type ISA. So as I explained, the complex addressing mode can be synthesized. So that means that it can be implemented using two default instructions. So this is the memory indirect load, and then we can implement this memory indirect load with the two load instructions. But we can find that. So as I explained, this instruction. So this instruction that supports the complex addressing mode just requires the two registers. But if we use the two default instruction, then we need to use the another registers like R3 here. And this is the example of the post-increment addressing mode. It's just the register number, required register number is the same, but we need more instructions. Okay. So this is the actual use of addressing mode. So why do I explain this? So even though the RISC type ISA support some more complex instructions, we can implement these complex instructions using simpler instructions, simpler multiple instructions. So like simple multiple RISC type instructions, but multiple. Why RISC type ISA is, so usually we can say that RISC type ISA is better than RISC type ISA because the RISC type ISA is very complex, and in order to support this complex instruction, the hardware structure should be more also complex. So we require more complex hardware for supporting complex instructions. Now, it's not good for the performance of a computer system. Actually, the performance of computer processors. So as I mentioned, if we use the simpler hardware, then we can increase the clock frequency. Also, that means we can increase the performance of our processor. So recently, like x86 processors, So recently, the x86 processors also use the RISC-like microarchitecture, which means that even though the x86 supports the complex instructions, because x86 is the CISC type ISA, these complex instructions are decoded to the several simple instructions. So these are called microcode. So by using this microcode, a single complex instructions are decoded into the multiple simple instructions. And then the x86 has the RISC-like micro architecture. And then simple instructions are only executed by this RISC type microarchitecture of x86. Because it's good for performance. So we can say that the most of the processors are RISC type processors, not CISC type, because of some hardware implementation issue. So, with the RISC type instructions, we need more instruction and then register spinning issues. So this is another example of some memory operands with some different type of instructions. So think like this. This is the high-level code like C equal A plus B. But we already know that when this statement is defined in our high-level language code, I mean that we need to first declare the variables C, A, B, C. So which means that the data space for variables A, B, and C are assigned in main memory, right? So which means that this data is originally stored in the main memory. And then in order to perform the add operations for this data, then the data should be transferred to the processor. It's the actually core, which means that it's the ALU of the processor. So it means the data transfers are required. So we can implement this statement using some different type of instructions or some different type of okay, so different type of instructions. Okay, so if we can some arithmetic instruction like add can access the data in main memory directly, then we can implement the instruction like this add CAP, and then this CAP just has the address of the variables A, B, C. Okay, so definition of this instruction is that the data is read from the main memory with the addresses of A and B, and then these two data is added, and then the result is stored in the C with the address of variable C. Okay, so we can implement the instruction like this. So which means that the operands of this add instruction directly use the data in the main memory. And what's the problem? Oh, I can use the large image. The problem is that this add instruction needs to access data with the address of main memory. But the address is very large, so the size actually this address requires the many bits. So for example, for the 32-bit computer system, we need to use the 32 bits for the memory address. And then actually, so which means that for the 64-bit computer, we need to use the 64-bit for the address, but it's not true actually. If we use the entire 64-bit address, then actually the memory size is very large. We don't need to use this very large memory in the computer system. So usually the size of the address bit is less than the 64-bit for the 64-bit computers. But for the 32-bit computers, you need to use the 32-bit memory address, which means that in order to access the data for these variables A and B and C, we need to be at least we require 32-bit multiplied by 3. So very large. So which means that we require very long instructions not to include the memory addresses. So another problem is that this data is not reused. So the data is stored read from the memory, and then the data is stored to the memory. So even though we use this data from A and B, this data is not stored in the register file. That's another problem. We can also rewrite the program like this, and so like this. This add instruction is the data from the variable B, and then performs the R1 plus B. Okay, and then the result is also stored to the R1. We can implement like this, but usually for the RISC type ISA, the arithmetic instructions does not access the data from main memory. And then actually the data access to the main memory is supported by data transfer instructions, like load or store instructions. So this is the familiar code for the A equal C equal A plus B. So actually the AB is transferred to the registers, and then it performs the add operation, and then the result is stored in the R3, and the result is stored back to the main memory using the store instructions. And exceptions. So what are exceptions? The exceptions means that exceptions mean exceptional events, right? Also, they can be false, like some divided by 0 or some unsupported instructions or some other instruction, some other false. So exceptions are actually rare events. Okay, so the divided by 0 is it's a kind of a false. So this event is very rare. It's a bug actually. So actually this is hardware need to support is rare events. Okay, like exceptions. Also, hardware need to support the interrupts or traps. So actually, exceptions are handled like branches or some jump instructions. So which means that if the exceptions are detected by hardware, then exception should be handled. But the exceptions are rare events. So usually the exceptions are handled by software, not hardware. So hardware just supports the detection of the exceptions, and then hardware generate some exception vectors, or also, which means that the exception vectors stores the causes of exceptions or why, and then some also exception information like the program counter is stored by hardware, and then the hardware calls the exception handler. So exception handlers are supported by usually operating systems. So the code in the exception handlers is executed, and then the hardware returned from the exception. That's how exceptions are handled by hardware. So exceptions are very similar to the branch instruction. But the problem is that the hardware needs to support the usually precise exception. So precise exception means that if exceptions are detected, then exceptions are handled by instruction order, not temporal order. So it's a precise exception. Also, the hardware specify the exact instruction that cause exceptions. Okay, so this is the precise exception. So usually it is required, hardware is required to support the precise exception. But it's not always true for all kinds of hardware. Some hardware cannot support the precise exception. Then in that case, the hardware just support some possible exception information, and then the software needs to handle these exceptions. So for example, the out-of-order processor, very old, the initial out-of-order processor cannot support the precise exceptions. Okay, so operating system needs to support this type of instruction. So these are examples of exceptions like I/O device interrupt, operating system calls like traps, and page fault, and then undefined instructions, hardware failures, and power failures. So these are kind of exceptions. And then these exceptions are supported by hardware. And then as I explained, hardware usually need to support the precise exception. So it's a synchronized with on instruction. So hardware need to specify which instruction causes these exceptions. Okay, so need to specify instruction, and then the instruction should be handled instruction order at the temporal order. Then the hardware must resume execution of the handler. Okay, that's a precise exception. Okay, so another some aspect of the ISA is the instruction encoding law. So that means that instructions should be encoded to the binary data. So actually, for the RISC type ISA has the fixed size, but the CISC type ISA, such as the x86, has the various lengths, instruction length. Okay, so these are also defined in the instruction set architecture manual. And then, so let's compare the RISC and CISC. So as I explained, so some main features. The main features of the RISC type ISA is that the first feature is the data in the main memory are handled by only data transfer instructions like load and store instructions. Also, another feature is that the size of the instruction length is usually fixed, like 32-bit for the ARM or RISC-V. Also, due to some instruction density, the ARM or RISC-V also supports the 16-bit instructions like ARM down or RISC-V 16-bit, the reduced instruction set. But usually the instruction size is fixed. But the CISC type ISA is different. As I mentioned, the CISC type ISA supports the very complex addressing mode. Also, the size of instruction is various. So, but the problem is that if we just consider the implementation issue, CISC type ISA is not good for the hardware implementation. So that means because the instructions are very complex. This type ISA requires complex hardware structure. It's not good for the performance. So, but you know, these CISC type ISA, such as the x86, need to support the backward compatibility, which means that even though, so we already know that these instructions are very inefficient for the hardware implementation, but we cannot remove the actually x86 vendors cannot remove these instructions. Because we need the x86 vendors need to support backward compatibility. But this to not support the inefficient instruction, then we require a complex hardware. It's not good for the performance. So this type vendors support this micro machine. So micro machine decode the complex instructions into multiple simple instructions. Okay. So then these multiple and so complex instructions are decoded. The multiple is decoded into the multiple simple instructions, and then actually the processor just execute the multiple simple instructions. So just and then as I mentioned, due to this micro machine, the inside of this CISC type processor actually is very similar to the microarchitecture of RISC type ISA. But you know, which means the processor needs to support this instruction decoding. Also, another issue is that the instructions, even though the size of instructions is very various, so which means that even though only one instruction is fetched from the memory, but this one instruction may generate the large number of instructions. So that is and then these large number of instructions need to build the instruction fetch queue of the this micro core. So it may occupy some large number of large amount of resources using only by one instruction. Okay. So this slide shows some important ISA and then some implementations like vendors. So system 370 is developed by IBM. It's the CISC type ISA. Then it's the most popular ISA. It's x86. So developed by Intel, and then it's also supported by Intel and AMD. So these are also CISC type ISA. And then, so also Motorola developed its own 800 type ISA. So you know actually the Motorola chip is used by Apple, but Apple does not use the Motorola CPU. And then you can find another RISC type ISA like Sun Spark and the PowerPC. It's supported by IBM and the Alpha, but we do not use Alpha CPUs. Okay, so it's the MIPS. So usually the MIPS is very popular, and then recently the RISC-V is also popular. So also we can find the ARM or RISC-V here. And then some very special instruction set is the IA64 developed by Intel. So and then you know the Intel developed this IA64 ISA, and then this is implemented to as the Itanium CPU. And then recently the Intel dropped the Itanium, like maybe 4 years ago, maybe. So this is also a RISC type ISA, and it's different from the x86. So you know, like Intel just developed the x86 ISA, and then actually the x86 ISA is the 32-bit ISA. And then Intel also know that this x86 ISA is very complex and then it's inefficient. So Intel tried to develop some very simple and then the advanced ISA called the IA64. So that is the 64-bit ISA developed by Intel. And then Intel tried to support to use this ISA instructions architecture, IA64, but it's not widely used. So the problem is that this ISA does not compatible is not compatible with the x86. Okay, so it's a very new ISA. It's efficient and then it's a very new, but binaries compiled using x86 ISA does not, it was or not executed in the IA64 CPU like Itanium. So Itanium was not selected in the market. So Intel dropped the Itanium CPUs. So it's a lesson from the history. Even though ISA was very good, but ISA was not selected from market. So it's a lesson from some market history. So actually the AMD, so you can find the x86 the Cisco legacy. So AMD developed the 64-bit ISA. So it's called the x86 60. No, x86 64 is the Itanium, actually 64. So AMD is called the AMD 64. So it's compatible with the x86, the 32-bit x86 ISA. So actually, so Intel now using this x86 AMD 64 ISA. Okay. So actually, so from now on, I will explain about the architecture, microarchitecture of pipeline the CPUs, and then out of other processors, and then VLIW, and then some other different type of processors. Then actually, I will use these instruction sets. So I frequently use these MIPS-like instructions. So if you see that these instructions, you can find that, these instructions are very similar to the MIPS ISA. Okay, so I will use these instruction sets. And then also, I think you can easily understand these instructions because these instructions are very similar to the RISC-V ISA we learned in the undergraduate course. Then some different instruction is the LS and then this S instruction. So these instructions support the floating point type data. So the LS means the loads single precision. So it just supports the store the data to the floating point registers. Okay, so also we will use some floating point instructions such as add.s is a add for single precision floating point, and the add.d is like double precision floating point. Then other instructions are very similar to the RISC type, the MIPS instructions. So I will use these instruction sets for the next classes. So for the next classes, I think I need to stop here. So for the next classes, I will discuss about the pipeline architecture also, the super pipelining, and then also I will discuss about some issues in the pipeline architecture, and then I will explain the out-of-order process architecture, which is very important for this course, out-of-order process architecture. So, and then I will explain these architectures based on this instruction set. Okay. So I'll stop here. Any questions? Okay, thank you guys. And see you in the next class. Bye.